diagram. Center of the reality of loyalty.
Thank you very much. Does it work? Microphone works? Sorry? Yeah. Okay, so thank you very much for giving me the opportunity to talk here. I want to explain commutativity of one diagram which I first want to write. Consider the three symplectic manifold.
Let me check that real quick.
No? It works?
No.
It's too far away? It works.
Let me go check it.
Okay. So we take a three symplectic manifold and we consider this diagram. I'll explain this diagram in this talk, but first of all, I first just write down. So this commutes. And this is a diagram of A infinity by functor. That notion I will define later on. But this is just one diagram, and this is the main theorem. And this is a part of the joint work with Evans and Rekiri. There are several earlier works, I will mention it later on. But first I want to explain these notations. So for the X to be a symplectic manifold, then we consider this category, and whose object is maybe triple, sigma, and L is immersed Lagrangian submanifold. It will have this emergence to X, and L tilde is a half dimension of X, and its symplectic form is 0. This is immersed from a submanifold, and sigma is let's say space structure. For simplicity, let me assume that this all are spin. X1, X2, X3 are spin, and the Lagrangian submanifold are spin. There are generalizations, but I need more a few more words, so I don't want to talk. And then the B is something called the bounding cochain. I will soon mention it. So this minus X1 is X1 with the opposite symplectic form. So this is a kind of a category of Lagrangian submanifold direct product. I think it appears in Maxim's law. And this is X2 cross X3, and you have this Lagrangian submanifold. And I will explain this construction soon, but there is some composition functor, which is kind of, you have this. So this is something called morphism in the Weinstein category, but since I include this B, then it is rather better to say it is unobstructed Weinstein category. It means that in the Weinstein category, the object is symplectic manifold, and the morphism is a Lagrangian submanifold. I just want to put some more information that morphism is a bit generalized to immersed Lagrangian submanifold plus something which I call bounding cochain. So that's something called that should be something called unobstructed Weinstein category. And this horizontal arrow is in a sense is just a composition of the morphisms in a unobstructed Weinstein category. So this is this first horizontal arrow. And this vertical arrow so this is for x, you associate this category. And then I have a kind of morphism from x1 to x2. Then you have a functor. So this is infinity. This is an infinity category, and this is infinity category, and this func is an infinity category of infinity functor. So the particular law means that you associate to this correspondence to this infinity functors. And this lower value, I'll explain it later, but this is a composition of infinity functor. So this means that, and the claim is that this is the kind of geometric compositions. In this unobstructed Einstein category, you define this composition factor. And then you go to downstairs, you have this category of infinity category and its functor, and it's a composition functor in this category, infinity category. And then everything is commute up to this homotopy. And that is the main theorem I just want to explain in this talk. But I want to go a bit more about this definition. So the goal is how I can prove it. But before defining, I just want to say the main idea is use this following diagram. This is called this diagram. And this is called a Y diagram. And this is due to this Kiri and Maxi Piansky. And this Y diagram is I just draw this. This is actually this domain in complex planes. I just draw three things: L1, L2, L3, and L13, L12, and L23. And Li is the Lagrangian submanifold of Xi, and Lij is the Lagrangian submanifold of Xi cross Xj. And you have this, you consider this man and some holomorphic map like this. And the idea is that you use some moduli space of a holomorphic curve on this domain, so that this gives some kind of boundary conditions, and you cook up some moduli spaces. And the idea is that this moduli space gives exactly the chain homotopy between these compositions and these compositions. But the chain homotopy between infinity bifunctor is actually rather complicated things. You try to write down what this chain homotopy means, and then you have a kind of homomorphism from many things to many things. And this diagram gives also rather kind of gives some homomorphism from many things to many things. And what's kind of funny surprise is that this many things finally just coincides, so that this commutativity exactly boils down to this diagram. So that's a kind of short summary of what I want to talk. Then I want to say a bit more about these definitions involved in this diagram. So first I just want to explain what is B. I mean, for this diagram to make sense, it is important to generalize the story to the immersed Lagrangians. I'll explain this point soon, but first of all, so we say that this is the immersed Lagrangians. So we consider this chain complex, something called the Fourier chain complex of this immersed Lagrangian. It is maybe some model, maybe that's a drum model. It's just a space of differential forms on this L tilde, X, L tilde, with some Noble coupling coefficient. So what this means? So suppose that L tilde is something like this. Right? You have L. So L tilde is S1 and L is this emergence. In this case, this one. In this case, this one is just a S1. This fiber product. In this case, S1 itself and 2 points. Right? Because this is the fiber product on X, so diagonal itself is the fiber product. But you have this extra things of this self-intersections. And self-intersection in this particular case corresponds to 2 points. And in more general case, you have a clean intersection, you have this submanifold. But so we take these ones. And then there's a work by Agaf and Joyce, and which somehow generalizes this our work. That this guy has an infinity structure. It's infinity structure. in general cut. So I mean, we did it in the case this embedding case, and Agaho choice generalized to this immersed case. We have still this APD structure on this extended Freer type chain complex, and this B is just an element on this CFL. And so this is a logical plane. So element is something like a formal power series. And lambda plus is the same thing, but lambda or this positive thing. And this B is an element here, so that this sum, so we satisfy this Molar-Cartan equations. So the object of this morphism, and object of this category is a morphism in unobstructed Weinstein category. So the morphism in unobstructed Weinstein category is a pair of this immersed Lagrangian submanifold, its spin structure, plus this B is the solution space of this Molar-Cartan element. So now, yeah. So I want to explain how. So the thing I want to explain is how to cook up this various arrows which appears in this diagram, and how we prove their commutativity. Is it possible to turn it down? Yeah, because I want to go back to this diagram for a while. Yes. So now I want to first define this horizontal arrow. So for the horizontal arrow is this, let me see, yeah. So this minus x1 plus x2. And yeah, before going to that, I think there's a previous work. I need to explain it. And there is a kind of Wertheim and Woodworth. And they do this kind of things, and plus and several related things. And the assumption, in case everything, all Lagrangian submanifold is monotone and embedded. And yeah, this is what Wertheim and Woodworth do, and also there's also some parties joint work with Mao. And yeah, so one thing, and also there's a work by Lekiri and Lipinski. The same case, but another proof. And I think they introduced this Y diagram I just erased for this part. And there is a work by Botman and maybe Wilhelm. Some attempt to generalize it, to remove these conditions. And you know, these are compositions. And why I want to extend it to this immersed case is if you consider compositions of Lagrangian correspondence, then even if you assume all the transversality, you can assume composition is kind of immersed. This Lagrangian submanifold is not closed. Embedded Lagrangian submanifold, if you compose two of them, then what you get is immersed Lagrangian submanifold in general. So they assume that the kind of this one and composition is also embedded. Then you can do this business, and also monotone. That's what this Wertheim and Woodworth did. And something I want to say that I can remove these assumptions and work in complete generality. That's what everything is compact. Okay, so now I want to mention how to. So the construction is this horizontal arrows. So there are various things I can say that so somehow this, if you consider object, say this L1, 2 is an around submanifold of x1, x2, and L2, 3, and minus x2, x3. Then this natural construction, I think this goes back to Weinstein. You can just take a fiber product, and you just perturb it a bit. This is a immense Lagrangian submanifold. So you just see geometry. At least you have this map as well as object constants. It is a kind of usual Weinstein category, or composition in usual Weinstein category. But the point is that we include this bounding cochain here and the bounding cochain here. So something is non-trivial is that suppose this L12 and L23 has a bounding cochain, then you want to cook up that this L13 also has a bounding cochain. That is some non-trivial point to establish. But but also not only that, you want to cook up this as an infinity functor, so that this is something about the object. So you need to say something about the morphisms. So you want to say how this Freire homology, Freire theory, kind of is mapped by this functor. So you have to do two of them, and then the way to do so is somehow by two steps. The step one is the following. So let's say suppose that this C is an infinity category. Then Ci. So let's see. So there is something called Yoneda embeddings. This is a kind of C module. So Yoneda. So this Che is a category of chain complex. It is a DG category, so it is particular infinity category. And this C op is the opposite category. And you know about the category theory, you have any category, they have an embedding from C to the kind of all functors from C op to the set. That's called Yoneda embedding. And you can do that basically the same business in an infinity category, so that all C is a kind of, it has this embedding. So what I want to do is the following things. So this is quite well-known things. So we just want to, when we want to define this, then we do it in two steps. One is just to construct this functor. So you have this f minus x1, x2 cross f minus x2, x3, which goes to the functor category of this f. So you just exchange it, then you just change it. This is actually, we have to construct this functor, and this is actually equivalent to have this something called a trifunctor. This is equivalent to have this trifunctor minus x2, x3 cross f minus x3, x1 to this chain complex. So this is equivalent. This is called a trifunctor. And this is a bifunctor. This is first step. I'll go back to this first step soon. But step two means that, so suppose you have an object here. Step two, so let me write this. This one is a comp. Then the step two is the following. Suppose that you have an object L12, B12, and L23, B23. Suppose they are the object of this. So suppose that this is an object of this minus x1 cross x2, and this is an object from this minus x2 plus x3. Then, as I said, that we have this. Then we say that we have this comp. This is L12, L23. Have this L12, L23, and then this is in this functor category. X minus x1 plus x3, and so this one is representable. by this L1 3 B1 3, and this is so the claim is that this B1 3 exists. This guy exists, and this L1 3 is this Weinstein's compositions. So this is the step 2, and I want to mention what this means. So as I said that the step 1 represent this here. So this is in a kind of image of this is in your kind this functor category, and this step 2 means that this image is contained in Yoneda embeddings. So you can just compose. So you have this Yoneda functor, inverse to Yoneda functor. This is Yoneda. And this is a kind of equivalence to the image. So not all functor may be representable, but if we know at least this image is contained in this image Yoneda embeddings, so you can just lift it. So this one you need to establish only for the object. Then if this functor is already an empty functor, and if you know that for the object concerned it is contained in the image, then you can lift it as an empty functor. So that's the proof here. And this is step 2. And actually, the step 2, once step 1 is realized, step 2 is actually can be done by some algebraic lemma. You don't need to go to involve geometry so much. There is some algebraic lemma, we can use it. And since I talked this story of this algebraic lemma several times last year, today I want to omit this step 2. And I want to talk this step 1 and also some other part of the story. So the step 1 is how to realize this trifunctor. So you have this x1, x2, x2, x3, x3, x2, x1. They want to this trifunctor to this category chain complex. So what this trifunctor means? So basically, suppose this means that you have this L1, 2, Lagrangian submanifold of minus x1 cross x2, and L2, 3, Lagrangian submanifold of minus x2 cross x3, and L3, 1 is Lagrangian submanifold of x3 cross x1. Then from these three, we want to associate some chain complex, which is actually a kind of infinite algebra of these three associated to these three Lagrangian submanifold. So we want to, from this, we want to associate some chain complex, L1, 2, L2, 3, L3, 1. So that is this construction of this trifunctor. And I draw one picture which gives this the way how we construct this trifunctor. It is this picture. We wrote this circular cylinder, and you draw three domains. So now, so you have these three domains, and I want to write this part is omega 1, and this part is omega 2, this part is omega 3, and I wrote this C1, 2, and this is C2, 3, and over the side, this omega 1 and omega 3 meet, so this is C1, 3. So we have this circular cylinder of infinite length, and you consider Ui from this omega I to xi. Let me remember, you have three simplex manifold, x1, x2, x3. Then this Ui is a holomorphic map, pseudo holomorphic map to xi on this domain. Then we consider the Cij. Then we consider this restrict Ui to Cij and Uj to Cij. Then this is a map to Lij. So this picture says you have these three domains, and each domain you consider holomorphic curve, but depending omega 1, omega 2, omega 3, the target is x1, x2, x3. Then suppose we consider here this C1, 2. Then you regard as a boundary of omega 1. Then so this one, U1, C1, 2 is a map to x1. And U2, C1, 2 is a map to x2. So this pair actually is a map to is a map to xi cross xj. And the boundary condition we require in these three lines is that this one goes to Lij. And Lij is the Lagrangian sum manifold of this xi, xj. So you have these problems. And so we can just consider the modular space of this harmonic curve. And this is a particular case of what this Wilhelm-Wood called kilt. So this is some particular case of this pseudo-harmonic kilt. And we consider this modular space. And the Fredholm theory and those things are kind of similar to the case of usual player theory. Then we get this chain complex. So this is CF, this CF L1, L2, L3 is cooked up from this one, but it's a kind of algebra. As a lambda 0 module, it is an element of this fiber product. I'm sorry, it's L1, 2, L2, 3, L3, 1. So L1, 2, X2, L2, 3, X3, L3, 1, and fiber product over X1. So this three Lagrangian sum manifolds, you take this triple fiber product over X1, X2, X3. And in a generic situation, this is finitely many points. And in more general, it's a sum manifold. So you take this one, then you take this, maybe tilde. And you take this chain complex. You take drum model, you take just drum complex, and the lambda 0. So this is this CF L1, 2, L2, 3, L3, 1. And if you see this, what happens for this modular space, and if you say that this harmonic curve has a finite energy, then if you see what happens when this asymptotic limit, when this goes to minus infinity and plus infinity, and you will see that you have an element on this triple fiber product. So if you know some Fourier theory, then you can try to do the similar thing in a Fourier theory. Then on this space, in the transversal case, there is a finite dimensional space. Then you count this kilt, you get this chain complex. That is this.
But you said chain complex, but that means d squared is 0.
Oh, I'm sorry. So I'm cheating. But if you assume that, so if you assume these three has a bounding cochains, then you can use some bounding cochains on these three lines to correct this error so that it is d squared 0. Honestly speaking, this gives a trimodule over these three things. So this is exactly what you want to construct. So you have this several of them that story the same. So you get trimodule, and you think about what it is a bit more. Then the result is that you have this something called a tri-functor. So this is this construction of the first horizontal line. I think this construction is known long time ago, this step 1. And actually, rather new thing is this step 2, which I say I don't want to talk. But the representability is a kind of issue which I couldn't go for a while. But now that goes. So this is a horizontal line. And then I want to consider about a vertical line. So vertical line is something like this, right? The vertical line is something like minus x1 cross x2, which goes to functional category, fx1 and x2. And as I said that this Wilhelm does more, cook up this functor in a situation everything is embedding and monotone. But their way is a bit different, but somehow they can do it. But then in our ways, this is actually a special case. Maybe I think it's better to say 2, 3, 6. This is a special case actually. Special case when this x1 is a point. Because this is something like a bifunctor. Right? So this is equal to this bifunctor minus x2 cross x3 cross x2 goes to fx3. But then we can just put minus point here and minus point here. Then this is exactly this first horizontal line. So it's kind of vertical line is a kind of special case of the first horizontal line. And is there any watch or clock or something here? Oh, I have a watch. sorry, yeah, it's very hard to see. Okay, yeah. So now so this is most of the constructions. I just work something here. So I explained this construction of this first horizontal line using this circular cylinder, and these two vertical lines are actually kind of special case of this horizontal line. So I want to explain this last lower line. It is more purely algebraic. So, but yeah, maybe I want to explain a bit because it takes me a while to understand this. So I want to explain these lines. So this line is something like this, right? So this is a purely algebra. Suppose you have this C1, C2, C3, there's infinity categories. Then there's something I want to cook up is a map from the C functor category plus functor category to this functor category. And as far as the object concerns, this functor is quite naturally constructed. You have an infinity functor from C1 to C2, and an infinity functor to C2 to C3. Then you can compose it to get an infinity functor from C1 to C3. And something is not so much completely clear for me was what happens for the morphisms. So this one is an infinity category, so that its object is an infinity functor. But its morphism is natural transformations. So this means that you have several natural transformations here, and several natural transformations here, and you want to cook up natural transformation here. And kind of in a couple of months, I try to find out explicit formulas how to define this infinity natural transformations, and I failed, and I still failed, but there is some other way to resolve it. Actually, there is a paper by I think Lukashenko, who says that there is some paper which called infinity category of infinity category, and I believe this one is constructed in that paper. But I want to explain the way how to do it because it is related to the proof of these commutativities. So the way to resolve this problem is the following. It is actually rather simple. So suppose you have this infinity functor C1 to C2. They have natural map from the C1, C2 bimodule. And yeah, cross C2, C3, and C2, C3 bimodule. So what I mean is the following things. Maybe the simplest thing is to explain. Suppose you have this A to B, you have this ring homomorphism. Then you can imagine B as a right B module and left A module, right? By this ring homomorphism. So you get A, B bimodule, right B module and left A module. So that's very well-known constructions. You can do very similar things. You have an infinity functor from C1 to C2. They have C1, C2 bimodule, which is right C2 module and left C1 module. That is this vertical constructions. And then we can so this is the arrow yet to define. So here you have the C1, C3 bimodule. And something one can easily see that this one is actually derived tensor product. So I mean, this is this. So what I'm doing here is rather easy. Suppose that you have a f from A to B and g from B to C. Then we have this B as a right A module and left A module, and C as a right C module and left A module. So we go here. So we take this tensor product. So B A tensor over B of C B C, and of course this is C over CK, and this is a composition, right? And this is of course commit. So and if you just look this commutative diagrams, and you can just try to kind of translate into APT language, and it is easy to see that this you get this diagram at least commutes as far as object concerns. Let me remind you that this one is only I define for objects. So this one commutes as object. But then next you see that this horizontal arrow derived tensor product, derived tensor. So this is the usual tensor product. But derived tensor product is I think like something like this, right? This bar complex of B. Right? So you take this bar complex in the middle. That's called derived tensor product. So, but then this is the derived tensor product, and actually it is easy that to lift this as an infinity function. This one is easy to make it an infinity function. And this vertical arrow is actually some kind of Yoneda functor. And we can prove that the vertical arrow is equivalent to the image. So we know that this is the infinity functor, this is the infinity functor, this is the infinity functor, which is homotopy equivalent to the image, and this commutes as the morphisms for the object. There is unique, unique horizontal arrow, which is the infinity function. So that is the definition of this function. So even I don't know this explicit formulas, you have this some canonical way to define it. So that is definition of this lower. So now at least I explained somehow how to define this diagrams. And the main theorem is I said that this diagram commutes. And so now I want to go back this Y diagram. So this is something called Y diagram. And I say that this is L1, L2, L3, and this is L1, 3. And maybe I just write it like this, maybe a bit bigger. Right. So you have this diagram. So this is exactly this domain in complex planes. So I draw this is omega 1, and this is omega 2, and this is omega 3, and this is C1, 3, and this is C1, 2, and this is C2, 3, and this is C1, this is C2, and this is C3. Okay, so this is the domain. Then I want to consider U map from here to this symplectic manifold. So you have this U1, Ui, which goes from omega I to xi. This is supposed to be pseudo-homomorphic. And we assume that you have this several things here. We assume that you have Li, which is the Lagrangian submanifold of xi, and Lij, which is the Lagrangian submanifold of xij. So we are given this guy. Then, so we have these three domains, and your U1 is here, which goes to x1, and your U2 here, which goes to x3, and your U3 is here, which goes to x3. You have a triple of the maps. Then we consider this Ui restricted to Ci, its boundary. And then I require that this image is in this Lagrangian submanifold. So this part goes to L1, this part goes to L2, and this part goes to L3. Okay, so now next we restrict Ui to Cij and Uj to Cij, Uj, yes. And then require that this image is in Lij. So this line should go to L1, 3, and this line go to L1, 2, this line go to L2, 3. So this is this moduli space. So you have a triple 3 harmonic curve to x1 and x2, x3. And on this boundary, you use this L1 as a boundary condition. Here you use L2 as a boundary condition. Here you use L3 as a boundary condition. And this lines, you have this matching boundary conditions. So now this is a space. And you know a bit about Fourier theory. Then usually we put several marked points here, like this. So now I want to say what this moduli space gives. It gives some map between several spaces, and that's I draw here. So this gives, this moduli space gives the following homomorphism. So first of all, so I will simply write it: B CF L1 tensor B CF L2 tensor B CF L3 tensor B CF L1 2 tensor B CF L2 3 tensor B means bar complex. Tensor CF L1 2 L2 tensor CF L2 3 L3 tensor CF L1 2 L2 3 L3 1, which goes to CF L1 L1 3 L3. So this is a map. So this looks rather complicated. What we do is the following things. We put various map points on each of these boundary points. And you put several kind of differential forms or any cycles on a Lagrangian submanifold, you put back by these marked points. That eats this bar complexes. So bar complex means that you have arbitrarily many points and arbitrarily many cycles associated to each complex. You cut it on this 1, 2, 3, 4, 5, 6. You have this 6 bar complex, you cut it. And then this guy, what is this guy? So this guy corresponds to this point. If you remember that something I introduced is this kind of moduli spaces, and you conformally change this lower half of this circular cylinder is exactly this point. So you have this situation, you have this L1 3, L1 2, L2 3. So you have these situations. And so the you put asymptotic boundary conditions here on this hole. That is exactly element of this triple chain complex, element of triple fiber product. And then you have this, you have more 1, 2, 3 ends. And here you have a situation, this L1, L1, 2, and L2. And it is similar to this circular cylinder, but one of them is just a point, so you can throw it away. So it gives this guy. So you get the element over here. And if you look this part, in a similar way you get element here, and the output is here, you get this element here. So I mean, you have some experience on this one with this kind of thing. This looks very complicated, but it is actually very natural thing to get from this complex. And you have various boundary operators, which can infinity structure, module structure, blah blah blah. A lot of structure. I don't want to write it, but if you just study the boundary of this moduli space, it exactly means that this map is in a kind of chain map for that complicated moduli spaces. So now, something I want to compare is the relation of this diagram and the relation of this rather complicated things. So something I can say the following things. So this guy I want to replace, not this functor things, but this is, I mean, using, so this arrow is used by tensor product, right? So we have this fx1, fx2 bimodule plus fx2, fx3 bimodule category, and this is the tensor, derived tensor product, and this is fx1, fx3 bimodule. So now we see that how this both sides appears on the factors here. And what is a very natural thing is that this tensor product is over fx2. So actually, so this guy, this one, so this tensor product is over bar complex, and this is exactly how this here appears. Because you take a tensor product of this x1, x2, and x2, x3 over this something on x2, so you have to take this bar complex of L2. That's exactly here. And then if you consider this vertical arrows, and the vertical arrows are exactly defined for this kind of diagrams. Right? This diagram defines this vertical arrows. So you see these 3 vertical arrows. Hmm? Yeah. So this 3, just corresponds to this vertical arrows. And then you consider this horizontal compositions. And horizontal composition is exactly this guy which appear here. And this complex actually corresponds to this horizontal compositions. And so we And then this map should be a bimodule. So this guy, this source is actually this guy. Right. And and everything should be a bimodule over this x1 and x3. This means that this factor appears here. And the reason that this appears is a bit tricky. This factor is actually appeared for the composition of this arrow and this arrow. Because in a sense we use tensor product of this x1 cross x3 to define these compositions. That's why this arrow appears. And if you look this, this is just too much a naive explanation, but I think it is impossible to explain anything more than that kind by talk. But if you just write down algebra correctly, then this looks rather complicated, but it exactly coincides to this chain homotopy between these 2 functors. So that's a proof of this commutativity. Okay. Yeah, so since I have some more time, so I was planning to talk something more. So, yeah. So now this is about this commutativity. And there are several similar things one can prove in a kind of related way. So the next thing is the following. So we consider 4 things. Then we consider this composition morphisms. A natural thing you need to prove is something like this. Probably let me write product I is 1, 2, 3, xi plus 1. Then this is x minus x1, x2, f minus x2, x4. Right? So we have to compose 2, 3, and 3, 4. It's here. And then you compose again, go to this x minus x1, x4. And here you take this f minus, right? X minus x1, x3, f minus x3, x4, and you compose another way. So you have this. So you have this 3 morphisms. Then you have 2 different ways to compose morphisms, right? Associativity. And the claim is that this is infinity associative as a infinity tri-functor. And the proof uses some diagram which I draw here. So maybe I need to picture. Yeah. So we consider this pair of pants. It looks something like this. And we draw a few lines. Probably I don't have enough color. One more thing, it should be something here. So I think this is not so much makes sense to explain what it is, but somehow this is omega to go to x2, x3, x4, and this is go to x1. And what is important is that here you have something like something which goes to x1, x2, x3, and this one should go something like x1, x3, and x4. And then you draw these pictures, and here you go something like which goes to x1, x2, x4, and this goes to x2, x3, x4. So we consider this coordinates, and you see that this guy x1, x2, x3 is responsible for this composition. This composition is kind of. We should have one more color. Yeah. I think there has to be something here. I'm sorry, how about it? This one is here, and this one should be here. And this one, this is 2, 3, 4. Right? This one is here, and this one is here. So somehow you just have this pair of bands twice, and you glue it again, and you draw several lines, and then this gives a coordinate between these constructions and these constructions. Probably my writing might be a bit wrong, but you can just basically draw some figures. And you just look these coordinates, then you can play with these coordinates and to put forward curve so that it goes to several x1, x2, x4, x3, x4, and this all the colored line are supposed to have boundary conditions on Lij. Then you have just some modular spaces, and you can calculate these modular spaces to get this commutativity. That is this proof of this associativity. Okay. So now I have some more thing to do. Okay. So now, yeah, maybe something more is about this transversality issue. It might be a bit, yeah. I was planning to say something about applications, but in a first talk, Konsevich gave some application already, so maybe I can just skip it and to talk more about that. Another issue. So now it is about this something about transversality. Transversality is a foreign problem. So let me consider this L1, 2, and this minus x1 plus x2, and L2, 3, minus x2, and x3. Then somehow the geometric composition should be this fiber problem. However, so how to do if this is not transversal? So you want to define this Weinstein category as an honest category. Then you have to deal with these problems. There are various ways you can say about the topological category or something like that. But still, you have to do something about this. And then the thing I can say the following things. So first of all, you take this P, say in Pij, on this xi plus xj to itself, this is Hamiltonians. Then we can just try to use this as a kind of P1, 2, L1, 2, x2, L2, 3. So this is always, you can make this always a transversal by using P. And the claim is L1, 3, phi, B1, 3, phi is equivalent L1, 3, phi prime, and B1, 3, phi prime. In this category, but after tensoring lambda. Actually, yeah. This one can prove, but one can say a bit. So I mean, what I mean is that you have to define compositions of the Lagrangian correspondence, unobstructed Lagrangian correspondence. Then this means that this is well defined up to as an homotopy class of the object. But this is a bit unsatisfactory because we have to invert the generator of the Novikov ring. And you know how Fourier homology works. That is understand what it is. But there are several things I can say. One thing is that there is no guarantee that L13 and L13, these two are diffeomorphic. Because P1, P can be quite chaotic. So they are theoretically equivalent, but geometrically they look very much different. This is one thing. And the other thing is that if we want to work over lambda 0, the story is slightly different. So first of all, I can strengthen a bit. So this tilde is something like this. L13 phi, B13 phi, this guy. But this is an unobstructed Lagrangian correspondence. So what do you mean Lagrangian correspondence? An unobstructed Lagrangian cobordism. So Lagrangian cobordism, it means that you have a kind of X cross this kind of, P star R, or this one. You have this L1, L2, next, then you have this Lagrangian submanifold on this one-dimensional higher things, which kind of give a cobordism between L1 and L2. This is called Lagrangian cobordisms. And obstructed means that you have a bounding cochain here, and the bounding cochain here, and you can extend it to bounding cochain here. And what is proved by Villan and Cornea is first they prove it in the case everything is monotone. If it is monotone, then Lagrangian cobordism does not change Lagrangian player theory. It is what Villan and Cornea proved. And I talked with them, and I think they agree with it's almost sure that this one, you have bounding cochain extended, then Lagrangian player theory is independent on this Lagrangian cobordisms. So this statement is stronger than this statement. And whether there is a gap with these two statements is a bit interesting, open questions. But I can say a bit more, and I want to finish a bit more because because we use this lambda. So I want to control what the lambda is below. So you see is a filter APT category. Maybe APT category over lambda 0. You have these two elements. And I want to define forward distance between these two objects. This is an infimum of epsilon, this is one property. You have this element Fg, F from morphism from C to C prime, and G is morphism to C prime to C. But you just have this T minus epsilon, and also T minus epsilon. This means that you allow some negative power of T, but only this epsilon. And we assume also that this Fg homotopy to identity in that places, and GF is identity in that places. So this is a definition of Hofer distance from object to pre-derivative category. Of course, if you take lambda in place of lambda 0, this implies that it is equivalent in lambda. But we can do a bit more strict. And the reason I want to call it Hofer distance is the following. So lemma. So you phi x is Hamiltonians, and forward, this is the actual forward distance between phi and identity is smaller than epsilon. Then kind of phi star LB, and this forward this distance is think forward distance of this LB is smaller than epsilon. We can prove it if you just look about this proof of this player homology type things. So what this means that if you want to define this Weinstein category, then you can make this deformation as small as possible. So for any epsilons, the object is well defined up to over distance epsilon. So something if you want to define this unobstructed Weinstein category over lambda 0, is something we can try to do is to construct the completions of your category. So problem is if C is an infinity category over lambda 0, then we have to find this C bar, embed this C bar so that this object is completions of this object of C with respect to this over distance. If you can do this kind of completions, then probably everything is well defined over lambda 0. This might be pure algebraic problem. I believe in the kind of situations we are working, probably we can make these completions. So this unobstructed Weinstein category defined in a kind of complete natural ways. Okay, so I stop here. Thank you very much.
Questions? Again, yes, let's change again. Resume at 2.